All right, we have here another projectile problem, and as I said, I think it helps to just sketch a picture here. So in this situation, we have a stuntman, and he's taking a ramp, and on the ramp, he's trying to jump a canyon. So not much of a motorcycle, I guess. It looks more like a bike. But anyway, the point is, he's hitting this ramp. It's at 45 degrees, and he's attempting to cross this canyon, which we're going to say is 100 meters long. And that's not really what a canyon looks like either, but bear with me. And we know he's leaving at a speed of 34 meters per second. All right, and that's our situation. So the question is he going to make the jump? But to do that, we're going to break down several things. So first off, this 34 meters per second is his total initial velocity. So we're going to call that VI. Not VXI or VYI, just VI because it's the total velocity. But let's see what else it's asking us for. So it wants to know what his initial y component of velocity is. So again, I'm looking for a velocity, so that means I'm looking for a v. I'm looking for a y, so that's vy. And it's the initial, so I want vyi to start this off. Likewise, I want vxi. And then lastly, how long is he in the air? That's time. And how far away will his motorcycle land? So how far is this going to get before he crashes or lands safely? Looking for delta x. So that's the first part of this. So let's go about trying to find out this vyi and vxi stuff. So I'm going to go to my equations, and vyi, I'm looking, and according to this equation, I don't have anything that says specifically vyi. Well, I do here, I suppose. I do here, but I don't have any of that information. I don't know delta. Well, I do know delta y. All right, scratch that. So I could use vyi here. However, I don't know how long he's in the air. I can't use vyi here because I don't know his final velocity. And so what about this one? This one I can use vy, and I can solve for it because I know v and I know the angle. And again, you might be confused saying, well, this doesn't say vyi. This means, when it doesn't say vyi or vyf, it means that I can use either. I can say vyi equals vi times sine theta, or I can use it for vyf equals vf times sine theta. It just means it can apply to either. So don't get thrown off by that. I know that can be confusing, but I'm going to use this equation. I'm going to find how large this vector is. Because if somebody's hitting this at 34 meters per second, what I'm really trying to do is if the angle here is 34, I want to know what is the y component and what is the x component. And this is where the trigonometry comes in, but I'm just going to let you use the equation. So that means vyi equals v times sine theta. So make sure you're in degree mode when you do this. So sine theta, so sine of 45 degrees, times vyi, which we said was 30, or vy, which is v rather, 34. So I get vyi is 24.04 meters per second. So in other words, his vertical component is 24.04 meters per second. That's how fast he's going vertically. Now, what is his x component? I'm going to use pretty much the same idea. Vxi is going to equal vi times cosine theta. And since this is 45 degrees, I'll just kind of jump ahead. They're going to be the same length. It's also going to be 24.04 meters per second. So in both directions, the initial velocity is the same. So he is moving just as fast vertically as he is horizontally when he leaves the ramp. That's what a 45-degree angle means. So we've got that solved. Now, how long is he in the air? So I'm looking for time. So if I look at my equations, I want to find one with time. So I can look here first, and I know Vx, and I might think I know delta x, but I just told you how long the canyon was. I never said he actually cleared it. So we can't use the 100 meters because it's not sure. We're not sure if he actually makes it. So that's not enough information to solve for time. This equation, on the other hand, delta y, vyi, gt, we do know everything to solve for time. We know his initial vertical velocity, we know g, and we know t, and we know delta y because we're assuming he's going to land at the same height he left. Delta y in that case would be 0. So we're going to use that equation. So we're going to say, we'll go to another page. So it's delta y equals, once again, vyi times t plus 1/2 gt squared. So So according to his delta y, remember, he lands, we're assuming, I guess this ramp is a little misleading. I should have made it smaller. We're assuming he's going to land at about the same height that he took off at. So we're going to call delta y 0. So that means 0 equals Vyi, looking back, was 24.04 meters per second. But we did not know time. So 24.04 t plus 1/2, so 0.5 g, which is negative 9.8 meters per second squared, times t squared. All right, so that's our setup. Let's start simplifying this. So 0 equals 24.04 t plus, so this is going to be minus 4.9 t squared. All right, let's get these on the same side, opposite side. So 4.9 t squared equals 24.04 t. I just added 4.9 t squared each side. All right, now, you might be saying, how do I solve for t here? I get t squared, it's a quadratic equation. But what I can actually do at this point is I can divide each side by t. And so what I'll end up with is 4.9t equals 24.04t. Now, 24.04, the t canceled. So now I solve for t, so t is going to equal 24.04 divided by 4.9. He's going to be in the air for 4.91 seconds. All right, so that's how long this motorcycle is going to be in the air. Now, that means that that's how long he's in the air before he lands. And during that entire time that he's in the air doing this arc, he's traveling horizontally. Remember, the horizontal motion is separate from his vertical motion. So if we know how long he's in the air, and we know how fast he's traveling, because remember, his x velocity never changes, that's one of the major rules of projectile, we can find out how far he's going to travel. And if we need to, we can look back in the equation for this. We know that delta x equals vx times t. The amount of time he's in the air times vx will tell us how far he travels. So go back, and we said vx was 24.04 meters per second. T is 4.91 seconds. So how far does he travel? Delta x equals 24.04 meters per second times 4.91 seconds. So we'll multiply that out, 24.04 times 4.91. And so his delta x will be 118 meters. So if the canyon is only 100 meters wide, then yes, he would land, he would clear this by about 18 meters, assuming no air resistance, which is why it's always probably good to be on the long side here. So that's the process. Again, a lot of equations to work with, a lot of steps. Take it one at a time, pause, make sure each step makes sense to you. I know, again, it's a lot to look at once, so just take it in chunks, but that is an angled projectile problem. This is one type. So until next time, I am Derek Genova. Have a delightful day.